So, the last class we were discussing what happens during the sampling phase, and in that connection we were looking at the noise model of a resistor. So, it turns out that if you have a resistor in thermal equilibrium with its surroundings at an absolute temperature T, then there is a noise associated with it. This is due to random motion of charge carriers inside the resistor, and the spectral density of this noise turns out to be 4 kT R on volt square per hertz. We will not get into the details of the math behind spectral density and such, but what I would like to mention here is that it is important to get a physical feel for what this means. And what this means is the following: if I took a resistor and monitored the voltage across it, I would see some random waveform. Now, if I took that random waveform and filtered it through an ideal band pass filter with a bandwidth of 1 hertz and a center frequency of f naught, there will be some waveform at the output of this band pass filter, is not it? Because you have taken a band pass filter, the input is some signal, the output is bound to be some noise like waveform. Please note that a band pass filter has two attributes. One is the center frequency, which in this case we have denoted by f naught, and the other one is the bandwidth, which is fixed at 1 hertz. Now, it turns out that if you do this experiment and measure the mean square value of the waveform at the output of the band pass filter, that mean square value will be 4 kT times R on volt square. The input has dimensions of volts, the output of the filter also has dimensions of volts. So, the mean square value has dimensions of volt square. Couple of things that one should notice. What is so striking about this relationship? The mean square voltage is 4 kT R on volt square, and the key point to note is that this is completely independent of the center frequency of the band pass filter. You understand? This means that regardless of what f naught is, as long as the bandwidth of the band pass filter is 1 hertz, the mean square value at the output of the band pass filter is simply 4 kT times R on. Is this clear? Okay. So, you can think of this as a sinusoid with roughly this power at, you can think of spectral density therefore in a very loose and non mathematical way as a sinusoid at that frequency, okay, with a power given by 4 kT R on, all right. So, since this basically means that regardless of f naught, if the mean square value is 4 kT times R on volt square, it means that as far as the input signal here is concerned, it means that it must have energy or power at the same concentration regardless of frequency. Finally, what is the band pass filter doing? It is taking a signal and only selecting those frequencies around f naught in a narrow bandwidth of 1 hertz. Now, regardless of what I make f naught, if I am getting the same power at the output, it means that the input process which is driving the band pass filter, right, has a strength which is independent of frequency, correct. Okay. Such a process is what is called a white process. Okay. So, this is white noise. The reason for calling it white is that it consists of all frequencies, just like white light, which consists of all frequencies. All right. Now, let us see what happens when I take the track and hold, it is in the track phase and the input is 0. So, track and hold in the track phase when the input is 0. Vn represents the what does Vn represent? Noise of the resistor, correct. All right. Now, during the track phase, therefore, the output voltage, even though the input is 0, the output is not 0. Why? Basically, as far as the noise source is concerned, it sees a RC network and the output voltage is the voltage across the capacitor. So, as far as the output voltage is concerned, it is nothing but a low pass filtered version of whatever noise there is in the resistor. You understand? And this noise source is often also called thermal noise because the origin of this effect is because of random motion of electrons, which depends on temperature. All right. So, physically speaking, this voltage is now no longer 0, even though the input is 0. There will be some voltage fluctuation there, and that voltage fluctuation is nothing but the noise waveform Vn filtered by a first order low pass filter formed by the RC network. Okay. Before we get into the math of what happens in the output, physically let us try and understand what happens when we open the switch. So, what do you think will happen during the hold phase? So, the switch was closed, it is in the track phase and the noise waveform of the resistor is something, and correspondingly the output is also doing something. Given the, if we know this waveform, we can compute the waveform at the output. Now, suddenly what are you doing? You are opening the switch. So, what do you think happens at the output? So, if you suddenly open the switch, which is what will happen when you go from the track phase to the hold phase, whatever voltage was there on the capacitor just before you opened the switch will tend to stay that way, correct. And do you think that voltage will be 0? No, because that depends on the noise waveform. So, what is this telling us? That even if there was no signal, because of the noise of the resistor, the output voltage is not 0, it is some random quantity because it is a function of the noise waveform. You understand? So, what I want to impress on you is the fact that even if there was no input, the held voltage on the capacitor has got a noise component. Does it make sense? alright. And given that the average of the input is 0, can you comment on the average of the noise component which is stored on the capacitor? The average value of the resistive noise is 0, correct. Now, first of all, why does this make physical sense? Or does it sound strange that the average value of Vn is 0, or it is not strange at all and this is in fact what you must expect? Pardon?
The noise is coming due to the motion of electrons.
Yeah,
so
all that
if
is
it
fine,
was-
it is coming because of motion of electrons, yes.
Let's say it moves one side, if it has to come back, otherwise, I mean,
Is there a more tongue in cheek argument you can give?
We are not giving any inputs.
So what? I mean, so is it with a battery, right? You are not giving any input, still the output of the
At t is equal to minus infinity, plus infinity, it is non-zero.
I didn't understand.
Since the magnitude is not tending to 0 at any point.
No, my question is the following: if I record this waveform, it turns out that the average is 0. Now the question is, does it seem reasonable that the average is 0, or does it seem unreasonable? Of course, it is a scientific fact, so this we can't dispute it, right? But does it make sense or does it not make sense? It makes sense, because if it wasn't, then there is no need for a battery, right? If the output average value is not 0, right, I will hook up 100 resistors in series, and the average values across the resistance will be some finite number from which I can generate power. Okay. So, since obviously that is not possible, it must mean that the average value must be 0, notwithstanding whether electrons are moving one way or the other inside. You understand? Okay. Now, given that the average value of Vn is 0, can you now comment on the average value of the noise quantity that is sampled on the capacitor? Please note that Vn appears in series with the input, correct. Just like the input is sampled when you open the switch, the post switch does not know what is input and what is noise, right. When you open it, it samples whatever is there on the capacitor is simply the voltage across it at that instant. In this particular example, it happens to be simply Vn, because Vn happens to be 0, correct. So, given that the average value of Vn is 0 and the output voltage is nothing but a filtered version of Vn, can you comment on the average value of this noise voltage which is sampled on the capacitor? It has to be 0. Is that clear? Okay. So, in other words, what we have seen now is that the held voltage has a noise component whose value is mean is 0, correct. So, if the mean is 0, I mean the other thing we would like to be interested in is what happens to the mean square value. Just like we are interested in the mean square value of Vn, we are also going to be interested in the mean square value of the noise component which is sampled on the capacitor. You understand? So, in other words, the average value of the noise voltage sampled on this capacitor here has got to be the same as the average value of the waveform that exists across the capacitor when the switch is closed. correct, because the switch is closed, you suddenly open the switch, whatever existed at that node before you open the switch is what is stored in the capacitor. So, the mean square value of the voltage sampled on the capacitor due to the noise is simply equal to the mean square value of the voltage waveform that exists across the capacitor when the switch is closed, right. So, how do we figure out what the mean square value of this waveform is?
Transfer function whole square. 2 KT.
Pardon?
After closing is steady state.
4 kTr into
Transfer function whole square.
transfer function whole square, and what is the intuition behind that? So, what is happening? The answer is indeed right. So, we have a noise source with some spectral density SV of f, which happens to be 4 kT R on whole square per hertz. Okay. Now, all I have done is taken this noise source and pass this through a filter which has a transfer function of h of f, and I am interested in finding the mean square value of this waveform. Clearly, this is a filter, a linear filter being driven by a random waveform. So, the output is also a random waveform which depends on the input as well as the impulse response of the filter or the transfer function of the filter, right. So, if we now go back to the intuition we developed with regard to what this SV of f means, that will help us get an understanding of how to compute the mean square value of the output voltage. So, what is the meaning of SV of f? What did we just discuss? What SV of f means is that if you take this noise voltage, conceptually pass it through a band pass filter centered at some frequency f naught with a bandwidth of 1 hertz, the mean square value at the output of this filter is going to be 4 kT R on, right. Okay. Now, if I took a sinusoid, right. So, basically if I look at this voltage and pass it through a band pass filter, this is going to be the variance, the mean square value. Now, if I took this, a sinusoid with this power, and pass this through a filter with a frequency response h of f, what is the meaning of h of f? It means that if I take a sinusoid and pass it at a frequency f, the output sinusoid will be at an amplitude modulus of h of f times the input sinusoid, or the power at the output of the sinusoid at the output of the filter will be mod h of f the whole square times the input power, correct. And what is the input power in a narrow frequency range around f naught, around some frequency f? In general, it will be SV of f is the power in 1 hertz around a frequency f, correct. Now, if I took this and pass this through an amplifier or a transfer function with a gain h of f, the power at the output will therefore be SV of f, which is the input power, multiplied by mod h of f the whole square, correct. So, if you look at the output pass spectral density, and this is simply the power of the output waveform in a 1 hertz bandwidth around a frequency f. Okay. Now, clearly the input frequency, the SV of f, that is the noise process, is white, which means that SV of f is independent of frequency, and that turned out to be 4 kT R on volt square per hertz. Okay. And what is mod h of f whole square for us? 1 by 1 plus omega square r square c square, and please note this is h of f. So, what should it be? 4 pi square f square r square r on square c square. Okay. So, in other words, S V out of f is this, and let us not lose sight of the units, volt square per hertz. Does this make sense to you people? The input noise source had a uniform power as a function of frequency. You pass that through a filter whose gain is varying as a function of frequency. So, it follows that the output power is the input power multiplied by square of the gain at that frequency. So, the output spectral density will be the input spectral density multiplied by mod h of f the whole square, correct. So, now what do you think would be the mean square value of the output waveform? See, what this means is that if I took the, what does this mean? Let us recollect again. If I took the output waveform, pass this through a band pass filter at a frequency f and a bandwidth of 1 hertz, the mean square value I get will be this quantity. Let us plot it to get some more understanding and see how will this look like. At DC, what will it be? 4 kT R on, and it will decrease, right, at 1 by 2 pi R on times C. What will happen to the power? It will become half. I will do this. So, why does this shape make intuitive sense? How is it that even though the input has a frequency content which is constant with frequency, why is it that the output frequency content seems to be decreasing? Pardon? There is a filter which is selectively letting only low frequency components get through. So, it makes sense that only the low frequency components of the noise are passed through with a gain of 1. As frequency increases, the gain is reducing, correct. Okay. Now, we can think of, so you can think of this as many sinusoids closely spaced together, right, each at 1 hertz spacing, and each sinusoid has got a power which is 4 kT R on times 1 by 1 plus 4 pi square f square blah blah blah. Does make sense? So, you can think of this as a whole bunch of sine waves all separated by 1 hertz, where each sine wave's mean square value or power, for a sine wave mean square value is the same as the power, right. So, the mean square value of each sinusoid is this quantity here. So, now when you add all these sinusoids, all of these are at different frequencies, mind you. when you add many sinusoids at different frequencies, what can you conclude about the power of the composite waveform or the mean square value of the composite waveform? Do you understand the question I am asking you? You have many sinusoids, right, all at different frequencies. Each one of these sinusoids has some power. When you add, when you construct a waveform which is the sum of all these sinusoids, can you comment on the power of this composite waveform? They will simply add up. Why? What happens if all the sinusoids were of the same frequency? Can you add up powers?
No, simply it is a periodic.
We have to add the roots and square.
No, if they are same frequency and same phase, then the amplitudes will add.
Correct. Okay. So why is it that now you say that I can simply add the powers?
Otherwise it will be open. If it's not
Simply Fourier
same
series.
frequency or multiples of frequency, then they are open.
I mean, see, you have a waveform V1, V2, V3 and so on, right. So all I am saying is mean square, I mean V1 square plus average value of V1 square plus V2 square plus V3 square is not the same as, in general is not the same as average value of V1 plus V2 plus V3 the whole square. When will it be the same? When all the cross terms become 0, and if you have sinusoids, when will all the cross terms become 0? When the two waveforms are of different frequencies, the cross terms all the average value of all the cross terms becomes 0. You understand, which is why you can add the powers. Okay. In general, if you just add many waveforms, the power of the combined waveform is simply not the same as the sum of the individual powers, right. Is this clear? No? Okay, let me just, what I was trying to say was, let us say I had a waveform A cos omega 1 t and another waveform A2 cos omega 2 t, right. The mean square value of this chap is A1 square by 2, the mean square value of this guy is A2 square by 2. Now let us say I add these two together, then I will get A1 cos omega 1 t plus A2 cos omega 2 t. What is the mean square value of this character?
A1 square by 2 plus A2 by square.
A1 square by 2 plus A2 square by 2 only if omega 1 is not the same as omega 2. If omega 1 equals omega 2, what is the mean square value? It will be 2A1, I mean, or A1 plus A2 whole square by 2. You understand? Is that clear? So even though a lot of you said simply you can add up the powers, that is only possible because all these different tones are at different frequencies. Okay. Now therefore the mean square value of the waveform at the output of the filter can simply be gotten by adding the powers in each infinitesimal bandwidth. Okay. So V out square average is simply integral 0 to infinity of the output pass spectral density integrated over all frequencies. Of course, you must bear in mind that none of this is, I mean, none of what I have told you is really rigorous from a random processes / communication point of view, right. But in this course obviously it is not possible for us to get into mathematical details of spectral density and so on. All that I am interested in giving you is some feel for why those formulae make sense. Okay. You understand this now, why the mean square value is simply the integral of the power spectral density. Now, what is the power spectral density? It is nothing but 4 kT R on, which is the input power spectral density, times 1 by 1 plus 4 pi square f square R on square C square df 0 to infinity. And we use a change of variable. So, choose for example 4 pi, sorry, if I choose 2 pi f R on C as u, then this integral simply becomes the mean square value at the output is 4 kT R on times df becomes du by 2 pi R on times C times 1 plus u square, and this integral runs from 0 to infinity. Is this clear? And magically we see that this is 4 kT by 2 pi into C, because the R on goes away. This is integral 0 to infinity of du by 1 plus u square, which is 4 kT by 2 pi C tan inverse u evaluated from 0 to infinity. What is this? Pi by 2. So, the grand result is that V out square is kT by . So, in English what this result means is that if I took a track and hold with 0 input, and a capacitor, the switch can have an arbitrary resistance, right, and because of the noise associated with the resistor of the switch, when I open the switch, when I transition from the track phase to the hold phase, the voltage stored on the capacitor is not 0, which is what one would expect for a noiseless situation. There is some random voltage on the switch. That random voltage is because of noise, right, and the mean square value of that random voltage which is stored on the switch on the capacitor is kT by C. Now, let us spend a couple of minutes staring at this and see why this might make sense. One thing that is very intriguing is that the mean square noise sampled on the capacitor is independent of R on, but what is the mechanism that is producing noise? It is R. So, it at first sight it seems somewhat strange that the resistor is the one which is producing noise, but magically the mean square value sampled on the capacitor is independent of the resistor, it only depends on the capacitance. Okay. So, why do you think this makes sense? Yeah, but clearly the final expression for noise has temperature in it. So, that is
This we have taken when the switch is open. So any R is not
is a good argument, but no, but please note that the value we are sampling, right, which is held on the capacitor has something to do with the resistor, is not it? So, why do you think this makes sense?
Impedance of the R is constant with the frequency.
So, what? So, in other words, the mean square value is simply the integral of the noise spectral density across all frequencies, which means that this is simply the area under this curve. So, if I reduce resistance, what is happening? Two things are happening. One, the peak spectral density is reducing, however, what other effect is? The bandwidth is increasing. Okay, so, the bandwidth has now become twice as it was before. So, if I reduce R by a factor of 2, this is what happens, right. And on the other hand, if I increased R, what would happen? The bandwidth will come down, the spectral density at DC will increase, right, but in all three cases the area under the curve remains the same. And why it makes sense is that if I increase resistance, it is true that the noise spectral density of the resistor is higher or lower? It is higher, because the noise spectral density of the corresponding to the resistor is 4 kT R, is directly dependent on the resistance. However, the voltage across the capacitor is not simply the noise of the resistor, it is that which is being filtered by an RC filter. So, if you increase the resistance, while it is true that the spectral density of the noise source of the resistor increases, simultaneously the bandwidth is reducing. The RC filter's bandwidth is proportional to 1 by RC. So, if the R increases, it is accompanied by a reduction in the bandwidth of the track and hold, and these two are effects which are working in the opposite direction, right. And it seems, I mean, it does not seem surprising that they cancel out, or rather, you know, while being an absolute constant is perhaps surprising, you can at least see that these are two opposing effects, and luckily they cancel out, okay, making the mean square value of the noise voltage held on the capacitor independent of the resistance of the switch, and it only depends on the capacitor. Now, what implications does this have on the track and hold design? what this means is couple of things. So, now if there was an input voltage in addition to the noise of the switch, right, which so let us denote model the switch as the noise source, its on resistance and an ideal switch. Okay. So, this is a real switch and I have here the sampling capacitor. So, the voltage sampled on the capacitor is V in of kT plus what is the voltage sampled on the capacitor? Plus some V n out of whatever kT, where the mean square value of V n out is independent of the resistance. So, in other words, the very act of sampling has already, what is this? What I mean, do you think this is a good thing or a bad thing? Ideally, what do you want to store on the capacitor? You want V in of kT. I mean, please do not mistake this kT for Boltzmann's constant, right, and temperature. This K is the index in time and T is the sampling rate, I mean sampling period. Okay. So, perhaps I think this is a bad idea to, I will call this m times I think n times T sub s, T sub s. Okay. Yes.
This R on cancellation is happening because it is a first order system, R on and C.
Yes.
Suppose it is becoming second order, then it will not cancel R on.
Well, so it turns out that it does. Okay, even if it is, I mean, what you are saying is, if you had a higher order system, does this cancel out? It turns out that it does. You can prove it, in fact, it is not very difficult to prove, but it can be, from what I have discussed today, you should be able to prove that that is indeed the case. So, if I take a general RC network and find the mean square value across the output of some capacitor, if I increase all the resistors by the same factor, it will turn out that if you measure the mean square noise, everything will, the increase in the spectral density will be compensated by the decrease in the bandwidth, and you will get the same mean square value. Okay. So, what I wish to point out therefore is that the very act of sampling the input on the switch, I mean using the switch and the capacitor, has already corrupted the input. You understand? And the degree to which it is corrupted is dependent on, is only dependent on kT of course and C. So, if you have to reduce the noise due to the sampling action of the switch and the capacitor, there are, I mean, there is only one choice in practice, right. I mean, you are often do not have freedom to change the temperature at which the system operates, and you can't change Boltzmann's constant, right. So, the only thing left is to increase C, and this makes intuitive sense, right. As we just discussed before we went into this discussion, we said that if the sampling capacitance is small, you are now signing up for getting easily disturbed by extraneous disturbances, and therefore, this does not seem very surprising at all, right. And what this is telling you is that if you make the capacitance bigger, the noise associated with sampling will be small. So, this makes intuitive sense, right. So, now can we answer the question, there are any number of choices of R and C which will give us the same tracking bandwidth, correct. So, is there, so now can we revisit that question we had earlier? We said that, hey, maybe we can choose a very bad switch with a lot of resistance and a very small capacitance, okay. So, what comment do you have now, given that we have had this discussion? So, if you get too greedy and choose use a very bad switch and a very small capacitor, claiming that anyway the RC time constant is what matters for a given tracking bandwidth, what you will end up with is that the noise component which is held on the capacitor after opening the switch will be large, okay. Since you have now added the noise to the input signal, it now makes sense to talk of the degree to which you have corrupted the signal by adding this noise, and a number, I mean what kind of measure do you is commonly used, I mean what do you think you can characterize. So, you can use a signal to noise ratio as a number to characterize the degree to which the sampling operation has corrupted the input, okay. All right. Before I get there, one minor point that I want to add is that, let us say you were sampling, right, you close the switch, you opened it, once you open the switch there is some noise voltage on the capacitor in addition to the signal. The next time again you close the switch to get into the track mode and you open the switch again, now you will have another value for the noise. Can you comment on the correlation between the noise you had earlier in the previous cycle with the noise you had in this cycle? They are uncorrelated. Why? It is, so what?
The autocorrelation function, you will have an impulse at 0.
Yes, I mean I agree that this noise source, successive samples of Vn are uncorrelated, that is absolutely correct. What I am asking for is not that, what I am saying is, let me draw the diagram when there is no input, Vn are on. So, at time instant n equal to 0, this was the state of the network and I open the switch. So, some voltage V n out of 0 is held on the capacitor. Then what do I do? For n equal to 1, again I close the switch and I open it again and I get Vn out of 1. Can I comment on the correlation between this voltage and this voltage? In other words, can we say anything specific about Vn out in the next sample, given that we know what it was in this sample? Yes? No? No, why?
capacitor voltage is like sampling the output of an RC filter whose input is a thermal noise.
Correct.
So if you are sampling right, then there is if the correlation has to be there between T and T plus T.
Correct.
That would be the successive samples here.
Correct.
Because the thermal noise is quiet and its autocorrelation function is a delta function,
Yes.
x of t into x of t plus t, that correlation will be 0.
That is for the input.
Input.
Correct.
No, but actually the time separated between t and t equal to 0 and t equal to t, they are the successive samples here. So
Not quite. Please note. Okay. So n equal to 0, we opened the switch, a voltage, the noise trapped on this capacitor is Vn out of 0. Then what is happening? We close the switch, then again what happens? The noise, the input noise waveform, right, is connected to the capacitor. What happens on the, so what is, so Vn out of 0 now behaves like the initial charge on the capacitor, correct, and so it is basically like having an initial charge on the capacitor and it is being driven by a noise source, and as he pointed out, between t and 2t or between 0 and t, the waveform Vn of t is completely uncorrelated and independent of what happened in the previous clock cycle, correct. But what happens to Vn out of 0, which was stuck on the capacitor when you began? It might or will. It depends on R on, correct. Might.
Can charge or discharge?
See, you can think of this RC circuit as having two components, right. There was, if you have an RC network and there was some voltage V1 on this capacitor, right, and there was some input, you can deal with the initial conditions and the input as using superposition, correct. This you are all in agreement with. Okay. So, let us see, since we are only interested in what happens to V1, I am going to say I am going to not worry about the input for the time being. So, if I have an RC network like this, what do you think will happen to V1? It will definitely discharge. It is not, it might discharge, it will discharge, and what is the time constant associated with the discharge? RC, correct. Okay. Now, can you comment on RC versus a clock period?
T V1 it should be 0.
Pardon?
clock period should be much
Very high.
So, the clock period must be much larger than the RC time constant, and why is that chosen that way? What happens if I mean, why should the clock period be much larger than? Please note that we are interested in having a high tracking bandwidth, right. The tracking bandwidth, if you are interested in sampling at a signal at a rate Fs, then the signal bandwidth is, the maximum signal bandwidth you would be interested in is Fs by 2, correct. So, in other words, if you want to have to be able to track a signal with a frequency as large as Fs by 2, it must follow that the tracking bandwidth must be much higher than Fs by 2, which is equivalent to saying that the RC time constant must be much smaller than the clock period, because the clock period is related to the maximum signal period, right, and if you want to track a high frequency corresponding to Fs by 2, the RC time constant must be much smaller than, yeah, I mean give or take a constant, must be much smaller than the clock period. Now, if the RC time constant is very small compared to the clock period, what do you think will happen to V1 between? Quickly discharge, which means that at the end of the next cycle V1 is completely discharged and the new voltage held on C1 on the sampling capacitor is largely a function of only the input waveform during that next cycle, right, which as we all understand is completely uncorrelated because it is a white noise. It is completely uncorrelated from period to period, which is why there is no correlation between, or virtually there is almost no correlation between successive samples of the output. Is this clear? Please note that will not be the case if the RC time constant is too large. If I deliberately choose the RC time constant to be very large, then what happens? There are two things happening. One, V1 is decaying, right, and the input noise voltage is trying to charge up the capacitor, correct. So, if the time constant is too large, then the decaying will not happen, which means that at the end of the second clock cycle the voltage on the capacitor has got some part of V1 plus something else, which basically means that the previous held noise and this noise voltage are related, which means that there is correlation. Does it make sense? But in practice we do not have to worry about it, because by design we would always make the RC time constant to be much smaller than a clock period, right. So, in the next class we will evaluate signal to noise ratios and then get to the implementation of a practical switch, right, which uses devices which you know very well, the MOSFET, right. Thank you. So,